Okay.
I need help. Sorry. Thank you.
Okay. Okay, so, ladies and gentlemen, we are going to continue on our discussion concerning the chapter 5 of the book today. But we're also going to get into a bit of a discussion more broadly of monads as time allows, although saving some of the bigger discussion of that potentially for a later time. So there's broadly sort of three big topics that I wanted to talk about today, all within this loose area. One, so it's actually chapter 6. I said chapter 5, but it's chapter 6. I wanted to talk a little bit more about how we're managing state and the notion of a function abstraction, this what's called in the book state, what I argued would be better phrased as state action, state transition, statement, as serving as a monad, serving as one of these constructs with a flat map and bind operator and observing certain laws. And I was trying to introduce how the book's code was accomplishing this, having the monad represent a statement or a state action in light of the limits on, in light of the functionality of flat map. And I got much of the way through it last time, but I wanted to finish up that treatment because I think it's important. We'll actually rehash some of it, so a few key points are again made. And then we'll go on and see some of the design choices, the alternative design choices, which we could use to capture similar functionality. And you'll see that how it's been accomplished actually has some real benefits to it. It may seem strange at first. It may even seem sort of strangely contorted, but it turns out it actually makes a lot of sense. We will then go on to see another monad, briefly, which is of significance when it comes to understanding the work with Spark, okay? And that monad is the future monad, okay? Future represents a promise to deliver a value from a future computation at some point in the future. It's a promise that you can hold and on which you could perform computation with the confidence that whenever that value becomes available, all those computations will be performed with it, okay? This is a future monad, yes, and it merits some reactions like that.
No, I mean, so you're basically saying it's like the idea of I have a function.
It's like an IOU.
Curried. Yeah, it's curried. That yes. I give it one thing, I give it another. The first thing I give it is a future, and I'm given the second value. I can then sort of reverse the currying.
I'd have to unpack that notion of reversing the currying, but that's interesting. Yes, you could think of it like that. I think I see where you're going with that. That's right.
But
yeah.
Generally, it's like literally like trading future options in a stock market.
Yes, that's right. And I was thinking about mentioning that. It's like an IOU. It's like, okay.
And you can pass this around to other people.
You can pass it around. They can perform computations on it, add it to things, map it, etc. And whenever the values come in, that will be performed.
That sounds amazing for networking.
So it is amazing for networking. It's one of the key use cases of it. So we're going to see future, and future is a monad, ladies and gentlemen. It's a monad. It contains a value, but metadata about that value, how to compute that value, which is critical. And then we're going to talk about sort of monads more generally, and some of that may go into next time. But I do have a big request for next time that I'm going to put up front, and I'll try to remember to reiterate it at the end, but it's so critical that I want to be sure that it's out to you early. Next week, we're going to begin in a big way with Spark. And I need you, if you're using a computer here, I need you to try to install Spark on your computer, okay? And you will find that you can go download Spark, and I'll see if I can point you to an appropriate location. But you'll want to download Spark as a package and install it, okay? And obviously it'll be a little bit different for Macs, PCs, and Linux boxes, okay? But we need to get that installed in your machine. Now, later, we're going to also, and probably won't be too much later, so you might as well do it at the same time, I think. You'll want to download and install what's called a Cassandra Connector, which is something Windchill alerted me to early on, but which is going to be key for our work, because we're going to be hitting databases stored in Cassandra. Okay, we're going to be using Cassandra to work with sample data from Ethica IAPI as part of our explorations. And so I'd like you to go download and install the Cassandra Connector. And it needs to be a Cassandra Connector that's compatible with the version of Scala. So you need to download the Cassandra Connector with the same version number as the Scala installation, or the Spark installation that you have in place, I should say. So this is something Windchill and I have gone through, and I have some notes on it, and Windchill's contributed in a very material way to those notes. We'll try to provide it to you, but the sooner you can get started on it, the better. And it'll provide more chance for maybe on Tuesday you bring a problem here and we can work it out. Okay. So one of the big goals for Tuesday would be at the end of Tuesday, I want everyone to have a working version of Spark and the Cassandra Connector, so that you can connect to Cassandra and we'll be able to query the databases as part of your projects. Okay, so that will be for Tuesday, and that will allow us to explore some additional monads in the Spark context associated with RDDs and data frames, these sort of resilient data sets, okay, which are going to know how to calculate themselves if they get kicked out of memory. And they're going to provide it's going to provide a nice sandbox for us to further take some of these concepts further and apply them to data science. Anyway, that's for next time. Okay, ladies and gentlemen, but I wanted to rehash some of the things we talked about last time in terms of important concepts from Chapter 6. Important concepts from Chapter 6 include returning state representations rather than mutating them in place. We have a functional way of handling state, which involves taking in some state, changing, updating that, but not, and then returning it. So rather than just changing it in place, you return the new state. If you don't return it, those updates will be not visible because the updates are occurring within a function. It returns back this new representation of state. So we have this kind of mapping from state in, state out, that's occurring along the way. And this is extremely powerful. If any of you are interested in taking it further, I would urge you to go take a look at continuation passing style in functional programming, which is a really, really nifty way to capture control flow within a functional context, and it's very powerful and actually critical to a lot of compilers these days. CPS style, its name. But the central abstraction here is a mapping. I mentioned it's called state, or it was called RAND. Do you remember RAND of A or RAND of int? Remember that? Okay, maybe someone could pass me the marker down there, which are also called elsewhere in Saskatchewan felts. Felts, yeah, because they have a felt tip. Okay.
They're calling cell phones because they have a cell in it.
Yeah. Okay, so remember RAND event, and then they generalized it in the chapter to be state of int. This is actually a mapping. This is, as I said, a statement or state action or state transition. It's not just the current state. It actually represents a statement. It's some computation, okay? And much of this chapter logically has to do with this notion of chaining computations together, chaining these statements or these state actions together. So you have one state action and you have another, and it gets composed to it so that one takes place before the other and passes its result to the next. And what is that result that gets passed like a baton from the first state action to the next? What is that thing that gets passed
State
on?
and a value.
Yeah, it's the current state. Yeah. So
More properly defined state rather than
that's right. That it's a true representation of state. This is a statement. So I disagree with this term that it's a state. It's actually, and if I had another color, I would show this in a different color. But really, I think it's a statement. I'm gonna describe it here and underline it to indicate it's different. It's really a statement. This is an action. Okay, it's an action.
a rule.
It's a rule. I like that. It's a transition. What is for Rand? What does this transition take in? Okay, the transition will take in something that's going to. Sorry. So here we'll go to it.
Generator instance.
It takes a random number generator instance, right? And so that is going to take that in, and it's going to map it to a what?
And then the succeeding random number generator.
And a random number generator out, right? So we're going to see this, that basically we're going to chain computations together successively so they occur one after the other. So computations that are like this, that are reading successive ints, for example, from the line, turning them into integers from the standard input, they can get read in. And this one will occur, and then the state that results from it will be passed on to this one. And the state that results from this includes the random number generator, critically. So that gets passed on to the next. Okay. Okay. So, ladies and gentlemen, we saw last time how this was achieved for Rand with flat map and with four comprehensions. So here we have flat map, and basically flat map takes in. Let's think about it in concrete terms, like a rand event, which represented kind of a certain action, and then it takes in a mapping here. What is A here? If we have rand of int, what is A?
Int.
It's an int. Takes in an int, and it maps it to what? To an action. This is an action. Okay, so this takes in an int, and it maps it to another action. And here we get out something that's a result of composing both of these actions, basically. So we're performing this computation here, and we are performing this computation here and yielding the result. Okay. This action here, what does it need to do its job? This M of B, what does it need to do to complete the computation? What does this need? M of B is a rand, so what does that need to do its job?
It needs
Random number generator. Once it has a random number generator, it's going to be able to then perform the computation step after step within it. Okay, and we saw how that could be defined with flat map last time here. So here we have an action that already exists. This is a rand, and here we have a next action which takes in a value here, and Where is that value coming from? This value here. Whence does that come?
The random number generator generates it.
Well, yeah, it's the value that was returned by this guy. So remember, each of these this is a rand here. And what is a rand? It's a mapping from random number generator to a pair. The second, the first element of that pair is an actual value. It's something of this type, t. It's a value. It's a number. What's the second element that this rand returns?
It's modified self.
It's modified state. It's sort of random number generator object. So that's the second value that this is returned. So this flat map, this thing t. Yes.
I'm just.
Yeah.
I'm wondering if there's any value in the realization that this is basically an HMM. Like, so an HMM, I don't know if we've talked about it in class, but like an HMM has a state.
Yeah.
And you transition between these states, and each state
That's
emits
right.
something, right? So this state emits a thing, and
Yeah.
so this is basically like this state. It returns the thing that it emits, and then the new state that it transitions to, so that state can then emit a new thing and transition to a new state.
That's true. Although there's the extra twist to it, that the thing that this rand of t, this rand of t is a function, right? It takes in a random number generator and it's going to return an int in a random number generator. This function, when it's given a random number, it returns this thing that you're saying it emits. This int. But it returns its state. But ladies and gentlemen, that int that it emits, that gets consumed by this guy to continue its job. That's what this guy is eating, right? This guy, this t here, it uses the value from this as well, right? It's using this value here. It's also using the random number generator that results from it. But this integer, it would be almost as if in the HMM, the thing that's emitted ends up being used in the next time step, the value that's emitted, as part of the state transition.
Yeah, I guess I'm just thinking that this is, I'm not talking specifically about this flat map part, but just the random number generator.
Oh, yeah, sure.
This rand in general is basically an HMM.
Yeah, that's kind
Although
of...
it's not like a limited number of states.
Well, exactly.
Not infinite.
It's not doesn't have a discrete number of states, etc.
That depends on the way the random number generator works. You can easily make random number generators any number of cycles that just cycles through the same number.
Well, yeah, but I mean, I guess what Kurt's fundamentally pointing to is that both of those have a very sequential structure, that at each point something is generated, and then the next state is dependent upon the previous state. And that's what you have here. Ladies and gentlemen, notice how this is defined. So this flat map, here we have, what do we have coming from this first rand? What do we have coming out of it? So we give this one an random number generator. What comes out? What's V2? What's the type of V2? An int. And what's the type of this guy? Well, it's a random number generator state, right? And then notice how it passes. Oh. Okay, I thought I fixed this last time. In fact, I was pretty sure. In fact, I was quite certain I fixed it last time. Oh, man.
You probably have evidence in the video.
That's why you.
Yeah, maybe. Ladies and gentlemen, so this guy here consumes this value that it omitted, this int, but also this random number generator that came out of it. Right? So why is it eating this guy here? Well, next action is a function from t. This is the value that was produced by this guy is now being used by this guy. How is it using this one here? Well, it's because that is fed to the rand. Remember, rand consumes a random number generator.
I don't understand what this function does.
What does this function do, ladies and gentlemen?
I mean,
it takes in. I mean, your map. You're doing a flat map theoretically.
Yeah.
Otherwise, why do you call it a flat map?
It is a flat map.
And
It's composing these two actions. That's what's going on. So
I don't see the two actions.
Okay.
The syntax is way too
okay. So
compact, if you will, for me to understand what's actually going on.
okay. So here's action 1. Here's action 2. We're invoking action 1. We are getting back from that. Well, action 1 is a rand. So we pass it a random number generator. That allows it to perform its action. It computes an int and a random number generator,
Okay.
which is then, both of which end up being used here. The int is used to compute the rand that results here. Okay, it's used to compute this mapping, and then we pass that mapping a random number generator, and what do we get out?
Yeah, it's just doing two.
No, we get out a pair of int and random number generator.
Yeah, it's
Yeah.
a new rand. It just does two rands in a row.
Yeah, it does these two rands in a row. That's what compose means. But the second depends on the value of the first.
Right, but
This is
where
great. I welcome these
where
questions.
would I
These are
do
great.
this? I mean, I don't understand what. I mean, you're
Where
telling
you
me-
will do it is it's being done right here, or it's being done right here. So let's
that
go
doesn't
back to
tell
it.
me anything.
So this is how you sequence computations with.
So this is a way for me to create a random number stream.
This is a way for you to create a stream of purely functional things where each takes in a state representation, returns a state representation.
Where I don't have to see the state representation in the meantime.
You don't have to see the state representation.
Okay.
It's automatically passed on from here to here to here to here, the state representation.
And
Okay.
because that was one of the issues I have with the chapter was that they get to this point sort of, and then they're like, well, now we don't have to actually show you the actual random number generator values being returned all the time. And I'm
That's
like,
right.
well,
So
okay.
let's look at it for this, right?
Okay.
Ladies and gentlemen, we could represent this. So this is a computation that involves successively generating random numbers
Mm-hmm.
and performing and returning a result based on those. Where are the random numbers? Just as a sanity check, where are the random numbers being generated here? Sort of show me the places where we're actually, generating a random number. Can anyone point them out?
Well,
Where are we pointing? Where are
can we
we?
define rand taking in a list of events? I'm not. That's. Ugh.
Okay, so this is good. This is why it's a hard chapter. So I really want to go over this. So, ladies and gentlemen, where are the ints being taken? Where are the random numbers being generated here?
Well,
If we had to look, which place here actually does something which generates a random number? I'll give you a hint.
Those flats.
Okay.
well flat map certainly does.
Yeah, but where is it in the? Where's the point where it's
INT
actually?
dot. I mean,
Yeah,
those are both-
this is generating this is something to generate a random number. Now, maybe what's going on is some of you are interpreting my question at a higher level or a more sophisticated way. I'm just trying to ask what things generate random numbers here if we look at it at a kind of naive level. Well, int does.
Because int was created earlier,
Yeah, it was,
right? It was value earlier as an int, as a rand, right?
yeah, I mean, basically, we're seeking, what this means is, hey, generate a random number. What this means is generate a random number here. And here we're generating what?
List random number?
A list of random number generators, and the length of, not a list of random number generators, a list of random numbers.
Right.
And the number of those random numbers is what?
The
It
first.
is the result of this computation. So itself was randomly generated. Right?
I'll put it this way. I think I would understand the for comprehension much better than this because
Okay. Yes. Well, this is exactly the point. So,
Right.
so, ladies and gentlemen, let's go and let's call up Scala and let's do something that's a little which puts it to practice. Let's get this to make it more concrete, so I can show something similar, right?
Sorry.
Import. No, this is great. We're going to import Scala. Util random. Sorry. Okay.
Incidentally,
Yeah.
I wasn't clear. I would assume that the Scala random functions like nextint and whatnot, are those purely
I'm
functional?
returning.
Okay. Okay, I'm going to compose her action with mine. I'm going to take this and put it away. So that's being passed on to me like a baton. Yeah, what's that? Sorry?
Is like nextint, all these things
Yeah.
that Scala gives us, are these purely functional?
Yes,
Okay, because it wasn't, so.
they're purely functional. Yeah.
But the problem is, well then how can I prove that? I mean, theoretically.
There's no side effect being performed that's externally visible in there, and the full computations are laid out in the chapter.
Okay, so theoretically, if I create.
It's a simple input-output mapping. You take in some things, you perform a computation, return them, but there's no updates to any sort of state occurring.
They're perfectly reproducible.
That's
They're perfectly
that's what I'm
reproducible.
trying- So if
Yeah.
I create a new rand, and I set the seed value, anybody who creates that with that seed value should get the same random number string out.
Correct. Yes.
Okay.
Yes,
And that's
exactly.
a really functional way of doing it.
Correct. Yeah.
You want to go
Okay.
Val?
Yes. No, that's correct. Okay. Okay. Here's the next integer. No. Now I find that a less than fully pleasant one. So I'm going to generate a random number between 0 and 100. Okay. An integer between 0 and 100. Are we okay? Ladies and gentlemen, now what I'm going to do is I'm going to generate a random number here between 0, another one between 0 and 100. Okay? There we are. Those are two random numbers, right? Now, there's something, though, a little bit disconcerting. Notice this is the same expression as that one,
Yeah.
but this one gave a different result. Why is that?
Because it's not referentially transparent or whatever.
Yeah, I mean that made it not referentially transparent. I can't every time I see this expression, I can't substitute in 63. That would give a problem. This updated some state behind the scenes.
Right.
Right?
That's the issue.
There's some state behind the scenes that this updated. And I'm going to show this computation, something comparable to, mumble. Sorry, mumble. Where's my, oh, okay. Oh, it's over there. Why is it over there? That's really weird. Okay, let me just move it over to this workspace. Boom. Okay. Okay, let's get over there. Boom. There. I'm going to perform this little computation here in the Scala terminal. Okay, so here we go. And what I'm going to do is I am going to go and I will do, so I'll do sequence, right? Sequence dot, and I will say fill, and I will have how many of them?
X.
X of them. And for each one, what am I going to generate?
Before you do your next string of y, but
Okay, so
that's fine.
for each of them, I am going to generate a next end, and I'll say of 100. Okay, just because I don't want. Yeah, I don't want to. I didn't want to have. Sorry. No. Sorry. I wanted to do this modulo what?
Y.
Modulo y here. Okay? Okay? What do you think will happen? What will come out of that?
Bunch of numbers between 0 and 31.
Okay. So this, ladies and gentlemen, this is a, I should really have made it this a vec. Is it vec or vector? Vector? Okay, fine. Here we go. Here's a vector of numbers. It's kind of the go-to collection for an immutable sort of indexed sequence of such things. And it's of what length? It's of a randomly chosen length, right?
Technically
X.
63, but
Yeah, but it was chosen by generating it from a random number, just like this is. We generated this and we used it and we called it value X. This is a flat map of this thing over it, and what this generated was a number, and we bound it to X, so we gave it the name X here,
Well,
and that's
but it
what this
also-
refers to.
But
Here,
it also
X.
generated a random number generator.
Correct.
And that was also bound as part of X and passed to the flat map to use to generate Y. Correct?
No.
Or
Close.
the random generator that was in
Close.
Y.
Close, but
Okay.
no. So flat map flat map isn't directly passed at just as it was past this. The thing that that flat map takes the thing that flat map takes as an argument
Mm-hmm.
is something that's a function from a number, which is whatever was the integer that was generated by this, to a rand. Okay, so this is X here is taking in the value that was generated by this. We'll get to where the random number generator, how that's sequenced, and that will involve something more than this, because this X is a name for the int that was generated. Okay.
Okay.
This Y is a name for this int.
I have a question.
Yes, question.
Int
Yeah.
dot. That int was
Yeah.
specified someplace in the code earlier than this.
Yeah, we'll see where it is. It's on page.
89. Says right on the slide.
Oh. Yeah, but that's that code. Int is actually specified a few pages earlier. So int is specified on page 84, where it says int is.
Oh, sure.
It just calls next int. Yeah.
Mhm.
And that call to next int is occurring on the random number generator that's shown on page 81.
Okay.
That they define this simple random number generator. Okay. So ladies and gentlemen, we generate a random number called X. We generate a random number called Y. That's what we've done here in Scala, although not in a purely functional fashion. And then we are creating a data structure of length what? X. That's what this is. And that data structure consists of, if you go look at ints is defined, ladies and gentlemen, at two different places. I think they go through successive definitions of it, the latter of which, as I recall, is left as an exercise to you, the gentle reader. But the earlier implementation of ints, I thought, was there, but maybe it's only one where they ask you to do it. Okay, so let's
Exercise 6.4 gives you the signature for it.
exercise 6
At
point.
the end of page 83 gives you at least the signature for it.
Okay, but it actually says implement ints that returns a sequence. So let's find this. So there it is. Yes.
6.4.
So exercise 6.4 on page 83. But I thought there was a later one which said go back and re-implement it with.
6.5.
That's improvement.
Okay, that's exercise 6.5 is for map. There, yeah, 6.7.
Yeah.
Use it to re-implement the ints function you wrote before. Okay, so ints returns like this non-functional thing in Java. This is a non-functional bit of code. We're calling fill of x, and that will create a data structure filled with these things. And I short-circuited a bit. What I should probably have done here to be a little bit more true to what's going on in the book is do this dot map that.
Right.
So first we create the data structure filled with x random numbers. That corresponds exactly to ints of x. And then I mapped each of its elements by taking it modulo y, and that corresponds to this thing here. Okay, so ladies and gentlemen, I've just shown you the code equivalent to this in non-functional Java. This is not referentially transparent. We can't take this next event and everywhere substitute 63. There's some magic going on behind the scenes here with state updating. Hey, look, Scala is a multi-paradigm language, ladies and gentlemen. It's a multi-paradigm language, okay? So here we have a collection of ints that are generated. Here we're generating 2 integers. Here, these are random numbers. Now, what's going on here behind the scenes, as Scott noted, is that somehow, magically, even though int is defined as something that if you really boil down to it, it's a random int, which turns out to be a function from random number generator to int comma random number generator. Even though it's of this type here, it's a function from a random number generator to a random number generator. Thanks. Ladies and gentlemen, on page 83, 84, you could see that this int call is defined as a rand of n, and that's simply a map, right? This is a map from a random number generator to a pair of ints and random number generator. Where did the random number generators go here?
They were used in the flat map.
They're being passed along secretly behind the scenes, and this is it illustrates it even more starkly, ladies and gentlemen, or perhaps one could say more beautifully. So here we are generating a random number. We're generating a random number x, generating a random number y. We're creating a data structure that consists of x random numbers, and we are mapping them. And all of this is purely functional. This is all in a purely functional language. Every one of these secretly takes in a random number generator and generates an int in a random number generator, but that's all being taken care of behind the scenes. Ladies and gentlemen, monads they're a container for values, and they consist of the value, yes, but lots of extra machinery to keep track of extra information. Here, what's the extra information being kept track of?
The state of the random number.
The state of the random number generator. In another case, it might be the coordinate system in which the value is measured. In another case, it's the unit in which it's measured. In another case, that extra information might be whether or not that number is computed yet, or whether or not it's meaningful, whether it's none or another value. Ladies and gentlemen, monads keep track of the contained value and data about that, metadata about it, or information state about it. Here, the random number generator. And what this is showing us is that with monads in Scala, we can achieve clarity, in terms of the syntax, by allowing the other information carried along, the random number generator, the coordinate system, or the state at which it's associated, or information regarding the units. We can carry that along in the background and focus our code just on the values being generated. And that all that extra information is being brought along. It is being carried along this thing is generating this int with, it's going to yield a different number than this one, because behind the scenes the random number generator is being passed along.
How do I retrieve that information?
It is being passed along to this. We'll see how it's being passed along in a minute, and you'll see that you can retrieve it very readily. Yes, Kurt.
So the fact that you have int there being called 2 separate times and generating 2 different numbers,
Yes.
does that not mean that it's not referentially transparent?
It's referentially transparent.
But if I take that int and just put it into a different spot, it's a different value.
No, if you were to take this definition of int and you were to put it in isolation outside of a for comprehension, what would you get? If you typed int,
What's going to give you it's a function.
it's a function, exactly. And it's suppose you were to put it this place, that place, that place, you'd always get out the same function.
Sure, but if I just copy that int and put it
Yeah.
into a different place, it's going to
Yeah.
give me a different number.
Within the for comprehension,
Yeah.
you're saying.
Yeah.
If I were to take this int and put it after this one,
Well,
it
X
would
and Y are
return a
different.
different number. Correct.
X and Y are different, but the code that generates it's visibly the same thing.
That's correct. Yes.
So what we've done is we've taken something that's the first version,
Yeah.
which is not functional.
Yes.
This is not referentially transparent.
You mean this version that I showed you
Yep.
here, for
Yeah.
example?
Yeah.
Yeah.
So we take that one, and then we're like, oh no, we want to make it better. So we generate this random number generator that then carries along the random number generator along the process.
Yeah.
And we're like, sweet, but then this is too much mechanism.
It's too wordy.
It's too wordy. I don't have to. The caller shouldn't have to always worry about passing along the internal state.
Yeah.
So then we abstract it again to get something not referentially transparent, but still under.
So
it's
I
still under the
understand your
surface.
perplexity, but I will assuage it.
Okay.
I will seek to assuage it.
This is my hope.
Okay. And it is a hope that is shared.
Well, it's interesting because
so-
if this is if this is referentially transparent, the issues that you're naming you're naming the same thing. The point is that if I call int twice in
Yeah.
succession,
Yes.
I will always get the same random numbers out that's referentially transparent. The first int will always be the same number. Okay, theoretically.
Correct. I could arrange this. But I want to. So I can respond. And Scott, you were starting to respond to that in one way, which is absolutely true. We always have recourse to the full state here. That's the thing. We can get access to the full state if we wish to enjoy it. But more than that, there's something deeper than that. There's something more powerful than that. There's something I would hazard more beautiful than that.
This gives us functional referential transparency with imperative programming.
That's true. We
And
can
that
mix
should
it with
be
imperative
released.
programming and still secure some referential transparency. But Kurt, I understand Kurt's thing. Wait a minute. So we're making it referentially transparent just to show that we can make it just as beautiful by making it non-referentially transparent anymore. But that's not the deep thing. The deep thing here is that, ladies and gentlemen, what you see here was baked in to the design of Scala, that it updates state behind the scenes, okay? Here, yes, we're happy to do it with int, but they instead could have shown as their example something to do with maintaining the coordinate information, or could have shown something to do with maintaining information about the units with which these are generated or what have you. The point is, we can do this not just with state, which is this special thing. I mean, in Java, ladies and gentlemen, in C, in C++, in C#, you pick your set of object-oriented or procedural programming languages. State, ladies and gentlemen, the current state of the system, that's something special. That has its own sort of metaphysical status associated with it. It has these special rules that it can be updated by a statement and carried around. But we can't shape the nature of that state. We can't use it to keep track automatically of certain information behind the scenes of custom interest to us. Here, we could maintain the same for comprehension to carry around not just random numbers, We could use it to carry around things like the units associated with things, or the coordinate systems, and we could add on in a modular fashion. Now we want to carry around with the values additionally this type of information or that type of information. We want to carry around the provenance information, what data sources were used to compute them, where they were computed within the program. We can add that in the background here, and it will be carried along transparently, and we can add it in a modular fashion. Say, we want to carry around with values all this extra information.
So, in other words, if we wanted to keep track
Yeah.
of where these random numbers came from,
Yes,
for example, the random number seed that generated the original random number generator,
that's right.
we can simply put that in there in the definition of rand list end,
That's right.
and it will keep it for every rand list end we have from now until doomsday.
That's-
So in other words, it's just like
Yeah.
you only had to change one line of code to get it.
That's exactly right. And suddenly we can modularly stick in the ability to keep track of additional information. But it's not just so that much is true. And I mean, at a deeper level, I think we're also allowing us to elect when. I was going to say we're allowing us to elect when to engage in referential transparency or not. I mean, we can always use this notation. And in this notation, what's going on is purely functional. This is, in fact, purely functional. It's just we're getting it to abstract up a level, hiding certain information from us. But it's purely functional. This is totally reproducible. We can go to this code and we can test it. We can compose it with other things. We can modularly combine it without worrying this magical state stored in the background. We can see the state or not as we see fit. And if we go and we unpack this notion of flat map, we will find that it's actually quite explicit about what's going on. It's taking the results of the first action and it's passing it to the second action. Now, Scott's earlier question, oh my gosh, oh, horrible. I fixed that too last time on the very tape. I don't, oh my gosh, oh no. Okay, say it ain't so. Give me a second if you wouldn't mind. I'm just going to, did I open? Oh no. Oh no. The fox is showing its tail. Okay.
Yeah, there we go.
Okay. State is a messy thing.
This is your slide.
Daring.
I'm sure the internet's laughing now as well. Okay. So, ladies and gentlemen, this is actually a function that takes in a random number generator. Why do you think I didn't get a PhD in art? This takes in a random number generator here. And you notice Scott was asking, does FlatMap take a random number generator? Not really. FlatMap takes this function from value here to we have to be careful here. Wait a minute. There's a bug yet. Where's the bug yet here? Where's the bug?
The return is not typed as we promised.
Okay. So there's a bug. What am I passing action here?
RNG.
Oh, I'm sorry. Wait, no, there's no bug. There's no bug.
Action
There's no bug.
generated
There's no bug. I was looking at next action. Next action takes in an integer. Where's this integer? Whence does this integer come? It comes from the results of this action, right? That's this V2 that came from action. We're passing it in to that. Where does random number generator here come from? It comes from here. But notice this next action function doesn't take RNG itself. This RNG, why is it that we're passing RNG here, the random number generator? It's so next action looks for an int. That's what came from this action. But why are we passing this random number generator to? What's consuming that? It's looking for an int. It's not looking for a random number generator. Where is this random number generator to get
Because
used?
next action v2 generates a rand u.
Yes. It generates a rand u. And what is a rand u?
Value of a random number generator.
Yeah, it takes in. It's a function that takes in a random number generator and returns a what? So the result of passing this v2 is what? The result of passing next action v2 is a what?
It's a rand.
Rand u.
v2 is just an int, so we get back a rand, right?
Right.
And then we pass the rand a what?
Random number generator.
Random number generator. What does it give back to us?
A rand.
Gives back a pair of an int and a random number generator. And you may say, well, wait a minute, this thing doesn't return a pair. This returns a rand u. But I would argue it does return a rand. Where's the other part of the rand u? What is the rand u besides the pair itself that gets returned here, the int and the random number generator? What else do you need to complete the rand u? A rand u is it just a pair? Is a rand u a pair?
It's an int and a random number generator.
And all the other information.
No. What is a rand u? It's not a pair, I'd argue.
Oh, it's a function.
It's a function. And where's the function here? So ladies
Rand
and
is defined.
sorry?
It's rand is defined as a function.
As a function. So this says basically give me a random one. If you give me a random number generator, then I'll pass it to this first guy. I'll get back a value and a random number. I'll then pass those two in turn to this guy, and I will end up getting back an int and a random number generator, right? And so this whole thing, ladies and gentlemen, is a rand u.
Right.
Its job in life is to take in a random number generator, do action 1, and using the results of that, do action 2. In other words, to compose them.
Okay.
And it gets back from that a pair of int and a random number generator object that returns it. So this whole thing is a rand.
Uh-huh.
You folks don't seem as into this as
I
me.
don't see why it's so magical. I mean, it seems to me like you're just doing two in a row.
Well, you're composing them. The thing that's magical is, if in my mind, the thing of beauty, that perhaps as you grow in age will make you too cry, is age and wisdom will make you cry, is that you can do this and hide the random number generator, and you can do that and hide the random number generator.
I don't get that step, I guess. Maybe I'll go back to the text.
Because this flat map is nothing more.
If you go look at the
Then-
function
then-
call,
then-
what does flat map return?
Flat map returns a rand.
Okay, in which case, why if this is the issue I have,
Yes.
and I think it's where you're trying to get to is, okay, if you go back to the for comprehension then, or the flat mapping.
Let's do this one at
Okay.
first, because that's.
So int is a rand, okay, and I'm flat mapping it, so I cannot just pass a number as an int. So I can't. That's
No.
not an int. That's a rand. Okay, fine. And then I'm.
It's a
flat-
rand. It's an action.
Right.
It's a statement. Int is a statement.
Mm.
It is a function.
And I'm flat mapping a function.
Yes.
Mm.
You're flat mapping a function.
So
young
that means
man.
that what I'm saying here is I'm doing f of x actually f of f of g, or I'm sorry, g of f of x.
Flat map is composing the functions. The first int,
Right.
the second int,
And then map the map.
and then ints. It is composing them. In other words, those are functions, and it is putting doing one after the next, with each one depending on the value of the previous one.
Right.
And it is constructed in such a way that these functions, you tell it to flat map, depend only on the integer. They visibly depend only on the integer. Things like this depends only on the integer, and the actual random number is being passed sort of secretly behind the scenes from one. Look at that. It obtained it from the first, and it's being passed to the second. And here it's taking it in at the beginning. It's being passed behind the scenes. So you can write your code in a way that focuses only on the contained values in the monad, and all the rest of the stuff can occur automatically around there. So you write your code when you're doing map or you're doing flat map on an option or on a try. You're writing your code with respect to the values contained there, and it takes care of all the magic about whether it's a none or a sum or whether it's succeed or try and so on. It's the same basic idea, the same basic beauty, I would venture. Here, give me just a second. Let me illustrate to you the fulsomeness of its beauty, or at least remind you of its beauty, right? Ladies and gentlemen, yeah, you don't hear this language in all computer science classes, I would venture. Okay, so
If some of you get an art degree, you certainly are concerned with beauty.
Okay. So, ladies and gentlemen, we can write something like that. Can we not? Right or not?
Sure.
You bet we can. Okay, ladies and gentlemen, could we write something like this? Like, would we do a map with this? Let's do something like this. Flat map of try of this dot to option, right? Could I write this? Oh, well, yes, I could, but it import Scala.util. Okay. There we go. Could we write that?
Sure.
Right or not?
Yes.
Right, indeed. Is that great or what? What's great about it is we can write our code with respect to the contained value, and it carries through all of the sort of particulars about whether, it's some value or not. I mean, look at this. We write our code, we say, we want to square the value, and it will take care of applying it to the option. In short, and in language that Winchell will appreciate, I think, but it's of significance, and it goes back to the earlier chapter, ladies and gentlemen. It goes back to the earlier chapter on page chapter 4, where the author talks about not needing to lift functions into this domain. We don't have to create a special square function all on its own for option. We can just say, hey, map this function, whatever function it is, onto a sum, and it will take care of applying it in the appropriate way into an option. Okay. So we could have given it this. We could have given it this. And we don't have to worry, option doesn't have a cubed function. We can just tell it, apply this function to yourself, and it takes care of all the magic making it an option and figuring out, okay, if this thing is a none, what will it return? Mumble. Okay, mumble. Mumble. Okay. Let me just do it like there. There. Okay. So, ladies and gentlemen, it takes care of all the wrapping and so on needed behind the scenes to apply this function to an option value.
Okay.
I don't have to create this function in a way that has to get entangled with, have to get keep in mind all the monadic stuff, all the stuff that's being accumulated about these values. Yes, it's keeping track behind the scenes. Does this value, is this a meaningful value? Yes, it's keeping track behind the scenes. What's the unit system of this value? Or what's the coordinate system with which this value is measured? Or where did this value originate within the program? Or what databases of information is this value using? Or how old was this value? When was it computed at a certain time? It can keep track of all that information behind the scenes, but I focus my programming on the actual values being manipulated, and all that stuff can be done on the side by it.
Right. Question, what does next int return?
To find the answer to that question, Scott, which is a fine one, by the way, I went through your many of these sort of soul searchings that you're doing right now.
Next int returns a.
It's page 81.
Yeah.
Page 81. Next int returns a pair of an int in a random number
Okay,
generator.
so if I type in next int here,
Yeah.
why do I get an int back and not the pair?
You'll get an int back.
Right,
What?
I'll get an int, but I won't get the random number generator.
Show me where next int is used here.
No, I meant like if you type it in the actual cursor,
Yeah?
like right
Yeah.
now.
Yeah.
If you type it
Yeah.
next int, you get an int back.
Yeah, but that's because we're not using the next int from this.
Okay, so my question was in the
Yeah.
implementation in Rand.
Yeah.
Okay, in the random thing in the Scala library,
Yeah?
next int doesn't return the random number generator. It returns just an int.
Because that's a different next
Wait, it's a different next int. This is, we're not, the
I get
book
that.
isn't using scala.util.random.
Right,
We
but-
imported Scala util.random, and it happened to call it next int. But they don't import that in this chapter. They're using the one defined on page 81.
Right, I get that.
Yeah?
But my problem is, how do I get the state of the random number generator out of this? Okay? How can I test whether or not this is working and it's referentially transparent if
Sure.
I cannot access the random
Oh,
number
you
generator?
can. You can. So the way you'd get it out, it's quite straightforward. First of all, you could call next int explicitly or return an int in a random number generator, right? A second thing that you could do, you'll notice that int on page 84
Mm-hmm.
is defined as a rand, right?
Right.
And it calls off to next int, by the way, to do its job. But if you pass it a random number generator, it will always yield the same results. Right? A given random number generator will always use the same results. So this int here always yields the same results, given the same random number generator.
Right. But how do I know I'm giving it the same random number generator?
You don't have to use it in a for comprehension if you don't want to, or you could have the for comprehension take in a random number generator which could explicitly be used to pass to this if you wanted to do so. So this could be embedded, for example, in a function which takes in a random number generator. And this code here, let's be clear, what does this code return? This might help address your question. This might even assuage your perplexity.
This returns.
What does this return? What's this whole for comprehension returns a what? Well, does it return a list of integers? That's very close, and so you've gotten a key part of it. But does it return a list of integers?
No, it returns a rand of list of integers.
Okay.
It returns a list of integers and the generator state at the end of it. Correct?
It's something more than that, which cuts to the heart of your question. Ladies and gentlemen, what does this for return? Scott correctly identified it, and building on this quite good suggestion of Haydn. Yes, there's a list of ints involved, but this is a rand of a list of ints. What is a rand? A rand is a what? A function. Ladies and gentlemen, rand ain't nothing but a function. What this is saying is that this is giving us something that's a function back. And with that function, if we give it a random number generator, as defined in page 81,
Right.
if we give it a random number generator, it will always yield the same result from this.
Right.
If we give it a different one, it will yield
It's a different.
a different result for that. But if we give it the same one, it will always yield the same result.
So this gives us a list of functions,
No.
a function of lists.
It gives us a
A function
function
applied to a
which
list of
takes in a function which takes in a random number generator and returns back a what?
A list of integers and this.
A pair of a list that consists, the first element of which is a list of integers, the second element of which is a random number generator.
A list of random numbers generated?
No, one random number generator to rule them all.
I mean, remember, a rand of A returns something of type A and the random number generator, not
That's correct.
a container of the same type.
That's right.
A variable of type A.
Right. Again, sorry.
Yeah, so ladies and gentlemen, this, I'm cautious about the variable comment, but it returns a value of that, okay, it could be a reference to it if that's what you were getting at. Yeah, so ladies and gentlemen, what this returns is something that takes a random number generator, returns back a list of ins, rand of list of ins, so this is a list of ins, and a random number generator. In general, if we have rand of t, what does this return back? If we had rand of t, what would this function be? From RNG to what? From random number generator to
TRNG.
a t, what? The t, comma, random number generator. So this is purely functional code.
Ooh,
It's,
whoa.
yes.
Okay, because the random generator you return is the random generator after it's gone through, or
Yes.
value, after it's gone through a random number of permutations. But since
Yeah.
we will, given a random generator spitting in, we
Yes.
will get not only the same list back, but the same
Yes.
random number generator state out.
Correct.
Which means this is referentially transparent.
Yes.
Okay, but we don't know going
Uh,
in exactly how many things we're getting.
So it's referentially transparent when viewed as a whole. But I think what Kurt was getting at,
No,
which
thanks.
which is it's an interesting point, is that if I look at this at a narrow level, and pardon me, Refi, as I approach the board, if I were to look at this at a narrow level, if I were to look at only that portion, or only this portion, just this by itself, or this by itself, or that, you could argue that it's not referentially transparent, because if I move it around within this block, I'll get a different result. But I would argue that as a whole, this whole thing takes in a random number generator, and it's totally deterministic based on that random number generator. If I use the same random number generator for this, it will yield the same result. So if I'm testing this code, and I want to have a reproducible test, I give it the same random number generator, and it will give me the same list, and indeed, the same random number generator out. Does that make sense? And in that sense, the whole is referentially transparent. We could substitute in this, and it will be totally reproducible.
Anywhere we see rand list int, we will be able to get, you can replace it with its value,
Yeah.
which is what referential
Yeah.
transparency is.
I have to say, I'm very impressed, because this is tricky stuff, and I can't tell you. I mean, you look at my annotations of this. I mean, some of you glimpsed them before. Every page of this, almost, you'll see sort of my tracing through the reasoning and so on. I do consider this chapter really, really challenging, and perhaps this is look at my notes in the margin there. It wasn't. If only Fairmont had put in such notes in his margin, we would be in a better place today. So, ladies and gentlemen, I mean, this is really tough stuff. But you've cut to, and due in no small part to your questions, you've cut to the chase of this. Now, what I did is I put together, and thinking this through myself, what are the real advantages over this? I mean, well, I wanted to think through what are the design choices. Okay, so given that we can do this, what's the advantage over just doing this in an object-oriented way, where we have modular information passing along? So each of these instead of having this kind of monadic thing carried around as a value, why don't we just do these computations not on numbers, on integers, we just do them on instances of some class. And within the class, we could maintain type information, unit information, coordinate information. We can maintain provenance information. We just add together units of class provenance int or what have you, and we're doing that. And you know, so I thought through some of the design choices here. And obviously, you could go down at the lowest level and put together a program. It's not obvious, but he discusses this in the book, the two authors. You could put together a program that looks something like this, and I took a little bit of liberties here, but you know, that you could have, okay, very explicitly, okay, I'm calling int, so I pass in a random number generator, and I get out these two things, and then I chain very explicitly this one, I pass into this one, and I get out a second value, and I pass in this this thing to this, and I get out a third value, and then I add them together, and I pair them with the final random number generator. This code could work, right? The problem with the code, this sort of code, is a couple-fold. I mean, it's verbose. There's a lot of, you know, we'd like to pay attention to what we're doing with the numbers, with the actual contents, but so much of what we're looking at is cruft associated with the random number generator. Now, we would like to maintain it in a way that it's referentially transparent. We'd like to maintain it in a way that we can always get reproducible results. But there's so much cruft here, there's so much extra stuff getting in the way of our appreciation of the code that it makes one wonder whether it's a good deal. But secondly, it's hard to write a pipeline in these sort of things. If I were to write a pipeline of sort of successive maps here, it gets kind of messy because we have to kind of piece apart the components of this and you know, sequence things and call things. It's kind of messy. We're operating with these kind of tuples, these pairs, and it's messy. You know, the approach that we saw earlier was this one here. This one here. This is what we've just seen, and it can lead to. It's conceptually straightforward, and it's greatly enhanced transparency. But it took a while for me and for this people in this class to really grok what's going on, and probably some of you will want to go back and watch the video a few times to see these comments, to really understand, to get your head around what's going on here. It's not easy, okay? The computations accepting the random number generators is sort of hidden here. And it's hidden, I would argue, in a helpful way. But what about the alternative of an object-oriented approach? So we have a class, and I'll call it value with random number generator state. It's a case class, ladies and gentlemen. So you give it an integer, and you give it a random number generator, and it has both, and then we could ask for int, for example. It'll give us back a value with a random number generator state. We could map something over it, you know, or return back this, etc. Now, one issue is here that, ladies and gentlemen, if we want to do a flat map, well, this is what the code would look like, right? Each of these, x, for example, VRS 1, VRS 2. These are all instances of this class. Okay? They're all instances. They represent a pair of a value and a random number generator state. We could do this, right? And we could say, okay, generate an int. And then, in fact, we could overload plus. So we could add them together, or we could just say VRS value dot value, VRS 2 dot value, VRS 3 dot value, and add them together and create a new instance here. Not bad. Conceptually pretty straightforward. One of the challenges here has to do with lifting. Okay? And the issue is, ladies and gentlemen, flat map is debilitated here. It's debilitated, I would argue. Why is it debilitated? Well, flat map, which is what we need to do this, This depends on flat map. Ladies and gentlemen, flat map here depends only on an integer, and it returns back this, right? It takes in. That's how flat map operated, right? It took in an integer and it gave a value back of that appropriate type. So that's what this does. But the problem is, ladies and gentlemen, f doesn't have access. It has access to an int, and that's great because we want to write our flat maps. Ladies and gentlemen, we want to write our flat maps here in ways that just manipulate the values. Eh? So here, ladies and gentlemen, flat map, it takes in an int and we put some result. That's how we would like it to be. But the problem is it can't be used for actions that depend on state. Why not? Well, ladies and gentlemen, it doesn't have access to the state. F doesn't have access to the state. What we give this doesn't have access to the state. Flat map does. Flat map itself does. But F cannot refer to the state of the thing. So you couldn't use it to flat map, for example, an option value that has none. It wouldn't know that it has none. Here, ladies and gentlemen, and so it turns out you have to write a lot of functions that could have been in principle written in terms of flat map. Instead, you have to write them explicitly for this class. Maybe a plus function, and a minus function, and a divide function, and stuff like that. And it turns out you can't chain together the computation of pipeline. That's very neat because you can't have f refer to the underlying state. Now,
couldn't you define those functions and then inherit this? Like this, you define those standard functions like plus and whatever, these lifting functions, and then just inherit all your objects from that function. Then you don't have to redefine them every time.
Yes. In fact, that's actually exactly that's something that monads kind of do.
Yeah, I'd have to think how to do that properly in a type-safe way with object-oriented programming. You have an idea there.
I'm not saying
and maybe
it's
with
better,
type parameterization, you might be able to do something like that. I'd have to unpack it because it's late. I want to draw attention to this. So interesting idea. So ladies and gentlemen, flat map here. How is it that, so I said here f can't refer to the state. It can't check is it none or whatever. So how is it it's any different here? Well, ladies and gentlemen, this code here, does it depend? So we here provide this here code provides an integer, right? So this depends only on an integer, I'd say. Does this result depend on the state of associated with this thing? Yes, sort of. I mean, we certainly get out the state resulting from action. That's what random number generator 2 is. It's the state compart resulting from action. Why can we do that? Ladies and gentlemen, it's because these things, this rand is a function. It is a function. I'll repeat that one a third time. It is a function. So ladies and gentlemen, we're able to do that because this whole thing here, whence does this random number generator come? This RNG2. Whence does that come? Where does that come from?
From the first action.
It comes from this first action here. Okay? And this action.
That first action is the input.
This first action is from this input. It's because this whole thing says, hey, give me a random number generator. And by the way, give me a random number generator and I'll do this for you. This random number generator actually isn't provided directly by flat map to next action. Only the int is provided to it. The random number generator is coming from the fact that rand itself, this rand of u itself takes in a random number generator. It's coming behind the scenes. It's not something we provide to this. So it's by virtue of the fact that this is a function that we're able to take in the state and use it to calculate the state coming out of that and use that to pass to this and get the state coming out of that. It's because this this is a function. And I would argue in a object-oriented way, you don't have that option. You don't have that option of sort of getting access to the state in this function f. Now, could we define a flat map Krugerian, or a Krugerian flat map, which takes in not an integer here, but it takes in a value with RNG state and maps to a value for RNG state? Yes, you could, but then you lose a lot of the benefits of being able to do something, ladies and gentlemen, like these sort of things where you can just operate on the values. So now there's not a lot of benefit for that compared to lifting functions directly into the state. So this is not a proof. This is not a watertight demonstration. It's just doing this in an object-oriented way has a number of shortcomings. And I would argue that to my aesthetics at least, this is actually a pretty good compromise for, at the one hand, having it be totally reproducible, totally referentially transparent from the standpoint of sort of modularity and being able to run this with in a reproducible fashion, a fashion that's deterministic based on a random number generator. But it's also very easy to read. It's very easy to kind of reason about, and it is modular. We could add in successive elements of the monads and keep track of all sorts of information all along the way, and we're writing code that still just depends on the elements that are being manipulated. And if you're writing long pipelines, ladies and gentlemen, if you're writing the sort of pipelines to which we may aspire within our course, and may I remind you, of these sort of pipelines. It was truncated in its fullness, but we've made use of some long pipelines in this class, and more will be coming. And that very first day, we made use of a long one. If you're writing long pipelines, the recourse to a nice, compact way of phrasing things is attractive. Okay, so monads, I'm not going to say that they are perfect. They're certainly not. They have their shortcomings, but they do have a real place in simplifying things. Okay, ladies and gentlemen, we're about to close, but I would like to suggest that you consider, and I have it here. I do have it here. Give me a second. There's this futures, okay? And here we go. I want to make sure I've opened the latest version of that. We're going to be talking about a different sort of monad, and this is going to allow us to handle asynchronous computation. Basically, they represent future values. They represent sort of a promise that I'm going to be getting a value, and we can characterize the computation that we want to perform regardless of whether that value is around or not. We can add things onto the computation. When that becomes available, we can use it. And this is very nice compared to so-called callbacks. Yes?
I said if not, and if the value is not available.
It'll just wait until it is and then use it whenever it becomes available. So suppose you want to wait for user input, for example, on a web form, right? Suppose you want to perform a search against Google, the Google API, and you want to get back results. Suppose you want to get those results and you want to harvest content from the URLs that are pointed to by the results of that search. So, when you search on Google, it refers you to different places on the web that are of interest. Suppose you want to get those values. Suppose you want to perform a sentiment analysis on the results. You want to analyze what are people talking about cigarettes here. Is it pro or anti-cigarette or what have you. Suppose you want to look up that, to do the sentiment analysis, you have a long-running algorithm. Suppose you want to look up into a dictionary about the most common words or summarize the sentiment. Ladies and gentlemen, we'll have an API which will allow us to perform those things. And just to give you an example of this, you could try this little code to whet your appetite. So I'm going to copy this into, maybe I'll just show it on the screen and then we can do it interactively. So ladies and gentlemen, we could, for example, say, okay, give me a future from going into this website and turning it into a string. Now this promise, this may be fulfilled within hundreds of milliseconds or so because it's able to go off there. But this could be some long-running query. This could be some long-running, request to a web server to perform an AnyLogic simulation. And this might not finish for hours. Now we could ask, okay, is the promise computed? But more to the point, even before it's computed, we could say, okay, map this in this way, do a flat map in this way, filter it, map values, and group with this in this way. And whenever this returns back, be it hundreds of milliseconds or be it hundreds of hours, it'll perform this whole computation on it. And we can pass this computation around, and tag things onto it. Okay, and maybe I will, because I am wont, to show you just a little bit of this right now, and I'm mindful of the time, but selectively choosing to ignore it. Okay, so ladies and gentlemen, we could go, we could just go here and import, we could import scala.io, scala.util.underbar, and then this concurrent execution context. So I'm just going to do those, paste, scala.util.all, and then there's the big kahuna, okay? It's this one here, scala.concurrent.executioncontext.implicits.global. Okay, here we go. Okay, come on. Frop. Okay, here we go. Ba-boom. And now I could do, sorry, I'll be right back there, Narcissus. I could do this, just to give you a flavor of what this looks like. Hey, I'll promise I'll get back there. Okay, come on. Okay, there we go. Watch this. What do you think I'll get back? Give you a hint.
Yeah,
This returns a string.
I'll give you a future string.
No, well,
yes.
but my point is that
Yes. Okay, ladies and gentlemen, it's a future of this. Now, watch this. If I say promise again, what do you think will happen? There it is. It's been filled in.
Is that the
Does it
full
say how
site?
long it
Sorry?
took?
Is that the full?
That's the page from the
is,
site.
Is that the full page? I mean, because my point is that if it's gotten some of it and not all of it.
No,
done,
it's the full page.
Okay,
It's
so
transactional.
okay, so okay.
It completed. It completed.
Serious?
Yep, it completed. But watch this. I could have said, dot length, right?
No.
Sorry, dot size. Sorry.
Put it within the future.
No, map it. I have to map it. Oh man, you folks are good. Dot map this thing dot length, right? I think that will work, right? Okay, so here's this
So now the
promise.
future
It's a
int
future of an
is
end,
string.
and when it comes back in the fullness of time, there it is.
So it's a future int now instead of a future
Yeah,
string.
and I could have meanwhile done this. Watch this. I could have. Now this would be a weird thing to do, but I could have said promise dot map of this times 3 or something like that, right? And if it hadn't been computed yet,
We would just say let's bracket.
yeah, exactly.
But here, what's interesting is that you have a future of an int that is equal to a list. The data types don't match until it
yeah.
completes.
Yeah, mumble. I agree. That's an interesting
I
thing.
find that very.
Maybe we can talk about that when we get into future success more cleanly.
Indeed. And perhaps we will defer that until next time.
Is that perhaps
That's
one way to detect whether or not something's completed, and whether or not the data?
No, you could just ask promise dot is completed.
Right, but I was asking, how does that actually work?
you know, and it can, I mean, obviously if the data types don't
Yeah.
match, then
Well, this is a sort of poor man's sign of that it's of a placeholder. But basically, this is the sort of API that will be able to operate on these promises. We can ask yes if they're computed. We can ask for their value, and if it's not yet completed, it will yield none. If it is, it will hold the try value. This will actually block to wait for the result with some timeout. So we could say, hey, you know, give me the results, you know, as long as it's within a certain time. We can map it, we can flat map it, we could filter it, we can collect it into possible values. It's a little bit like a map and filter at the same time. We could say when it's completed, when it's ready, do this thing, like perform this action with it, like store it to a database. And we could say if it succeeds, when it succeeds, do it. When it fails, do it.
why do I need on complete?
Sometimes it's nice to be able to alert the user, among other things, that it's complete. Update a progress bar, stuff like that.
I mean, if I want to write the thing
Yeah.
to a database once it's complete, I
Yeah.
shouldn't have to call on complete. I should just
Right.
write the extra the pipeline.
Yeah, you could do that. That's correct. Yes, you could do that. Although you might handle on failure and success separately. You might elect to handle them separately. So, ladies and gentlemen, futures. Futures you can imagine being very useful when you have distributed computation on resources. You can't be sure exactly when it will be computed. You can use a future to represent it, and when it's available, it will be given to you. And meanwhile, you can characterize all your computation that you want to perform. This is a monad.
I am very interested in using this literally as a modeling tool.
I'd be very interested.
Because I could model promises as futures.
Yes.
Okay, like inside my
Yep,
model, and
that's true.
and then I could value them differently. For example, than
Mhm.
the actual transaction. Like, oh, I promised to pay you back on Tuesday for a hamburger today. I could actually write that
Yep.
in specific language.
That's true.
That the language itself can actually deal with.
That's right. That's right.